In this video, we'll be discussing the concept of gravitational potential and escape velocity. All right. First things first, let's take a basic definition. Let's start with the first one there, gravitational potential. Now, gravitational potential, note that this one is represented by V. All right. So gravitational potential is actually represented by V. All right. By definition, gravitational potential at any point on the Earth's surface is the work done in moving a unit mass from infinity to that point. All right. That means the gravitational potential at any point on the surface of the Earth is simply the work done in moving a unit mass from infinity to that exact point on the Earth's surface. All right, so that's how we define gravitational potential. Okay, mathematically, gravitational potential V is expressed as the ratio of the product of the universal gravitational constant multiplied by and the mass of a body to the distance traveled. All right, so basically this is the formula for gravitational potential. Okay, some authors will put a negative here. They'll tell you it's minus gm all over r. Okay, the negative means that the mass was being brought from infinity to that point. All right, but it has no effect in your solving. So we can leave our formula as gm all over r. What is the SI unit for gravitational potential? All right, the SI unit for gravitational potential is actually joules per kilogram, right? So this one is measured in joules per kilogram. So we have this as J per kg. This is the SI unit for gravitational potential. Okay, I'm just going to prove why this is so quickly. So let's prove that the SI unit is joules per kilogram. So how does this give us? How does Gm over R give us joules per kilogram? I'm going to prove this very fast. First things first, this is equal to G, which is the universal gravitational constant. The unit is Newton meter squared per kilogram squared. That's for G, as we said in our previous class. We also have mass here. This mass, the SI unit is in kilogram, so kilogram all over. This distance here, the unit would be in meters, so we have this. All right, let's see how we can play with this. If we play with this, this would be equal to, let me rewrite this as Newton meter squared all over kilogram squared. So you can see it clearer. This times kilogram, this all divided, of course, by meter. So this is a better expression of that. Okay, all divided by meters. And this would now be equal to Newton meter squared all over kilogram squared times kilogram. Of course, we said to eliminate the division, we turn this to multiplication and we take the inverse of this. That becomes 1 all over meters. So we have this. All right, if we do this, this will be equal to, from here, kilogram will cancel one of this. I'm left with kilogram. Also, meters cancel one of this. I'm left with meters. So I'm left with Newton times meters, which is Newton meters all over kilogram. Now remember that the concept of work done, right? We said gravitational potential is the work done in moving a unit mass from infinity to that point, right? And we said from work done is simply force times distance. Force in Newton, distance in meters. So force times distance becomes Newton times meters, and work done is measured in joules. So it means that Newton meter or Newton times meter, if you want to, is the same thing as joules. So that means this Newton meter here can be expressed as joules. So we are now having joules per kilogram. So basically, this is how we get the SI unit of gravitational potential as joules per kilogram. Okay. All right, then let's take an example on this. So let's say let's take an example on this. So in our example, let's say we asked to find the gravitational potential at the Earth center. All right, let's find the gravitational potential at the Earth center. Recall that we said gravitational potential is V equal to G M all over R. If you're taking the Earth center in question here, that means the M becomes mass of the Earth and R becomes radius of the Earth. So we have this. And since we already know the value for ME, that's a constant, that's mass of the Earth and radius of the Earth, we'll simply put those values here. This is equal to the value of G is a constant, whose value is 6.67 times 10 to the power minus 11. That's the value of G. ME is simply mass of the Earth, and the mass of the Earth is also a constant, 5.98 times 10 to the power 24. That's the mass of the Earth, all divided by the radius of the Earth. So all divided by radius of the Earth. The radius of the Earth is 6.38 times 10 to the power 6. So we have this. All right, so let's get this done. I'll just simply get my calculator and punch this directly. All right, so 6.67 times 10 to the power minus 11 multiplied by 5.98 times 10 to the power 24, all divided by 6.38 times 10 to the power 6. So if you punch this, the answer is about, you have this as 62518,181.82 approximately in joules per kilogram. Let's express this in index form. From here we have 1, 2, 3, 4, 5, 6. All right, 6 is actually a mega. This is equal to 62.5. Okay, so points here, 62 point. The point comes this way here. 62.5 approximately becomes 52 because 8 gives you a plus 1. 1 plus 1 gives you 52 times 10 to the power 6. We moved 6 times, right? 1, 2, 3, 4, 5, 6. All right, times 10 to the power 6 joules per kilogram. And if I should work on this, 10 to the power 6 is called mega, right? It's a mega, it's called mega, it's a prefix. Mega is a capital M. If I attach it out here, we'll have that V, it's equal to 62.52 times 10 to the power 6 becomes mega. That becomes mega joules per kilogram. So this becomes the answer to this question. So basically, this is how we solve problems on gravitational potential. All right. So always recall your formula as Gm all over R. Okay. All right. Let's look at the next concept. They're called escape velocity. All right, so let's look at the next concept called the escape velocity. All right, escape velocity, by the way, is abbreviated by V subscript E. Right, so V is gravitational potential, while escape velocity is V subscript E. Now, a definition: escape velocity is the minimum velocity required for an object to just surpass, which means to just escape or to just leave the gravitational influence or field of an astronomical body, example, the Earth, permanently. All right. So, for an object to surpass the gravitational influence of a field or of the Earth or of another planet there, it must have, or it must be projected, or it must move with a particular minimum velocity. Now, that minimum velocity that the body must move to surpass the gravitational influence of a particular field or an astronomical body is called the escape velocity. All right, let's look at the formula for escape velocity. All right, to derive a formula for escape velocity. All right, so we'll use this diagram to derive a formula for escape velocity. Let's say we have a mass that was previously at this point here. All right, this mass escapes from the Earth. This mass escapes from the Earth to this point. All right, let's use this diagram to derive the concept of escape velocity. So first things first, if we have this kind of a diagram here, something of this nature here, the force of, from Newton's law of universal gravitation, the force of attraction, of course, there will be a force of attraction between this mass and the Earth. This is the Earth, all right, and the Earth. The force of attraction between them, no matter how small, right, will be equal to, from Newton's law of universal gravitation, F will be equal to the universal gravitational constant times the product of the mass and the mass of the Earth all over the distance of separation, which in this case is r. That's this r here, right, between the Earth and the mass. That's r. All right. So all over r. So I'm having all over, of course, r squared of the distance between them. All right. So this is the force of attraction, no matter how small it might be, between the Earth and the mass. Okay. Now this is one. Next up, um, the work done in moving this mass. Now we said this mass is escaping the Earth, all right? So the work done in moving this mass from this point to this, all right, a work has to be done because a force, all right, is moving the mass out of the Earth. Okay, so that means a work is done. The work done, recall that we said work done, right? The work done in moving the mass out of the Earth is equal to, now work done usually is force times distance. That's work done. All right, so for this case here, we've already gotten the force here as gm. The force here is gm me all over r squared. That's the work, that's the force times the distance. As you can see here, is actually r. So you can see the distance it has covered so far is r. So this times the given distance here is r. So with this, we can say that the work done, w, would be equal to, from here, r cancels r squared. We have r, would have this as g m me all over r. So this becomes the work done in moving the mass, or in trying to move the mass to escape the Earth's gravitational pull. Now, for us to have the value of escape velocity, the condition is that if I'm moving a particular mass, right, out of the Earth's gravitational influence, one of the things to note is that as I'm moving the mass, that mass will possess a kinetic energy. Of course, we said kinetic energy is the energy possessed by a body in motion. All right. So if a body is leaving the Earth or leaving the Earth's gravitational pull, it must possess a kinetic energy, and this kinetic energy must be equal to the work done, all right, in moving that mass out of the Earth. So we are saying that in this case, kinetic energy, the body possesses kinetic energy because it is being moved, all right? So the energy possessed by a body in motion should be equal to the work done in moving the mass out of the Earth. We've already gotten a formula for work done, which is this one here. This one here. Let's get a formula for kinetic energy. We'll just call this, let's call this equation asterisk if you want to. Let's get a formula for kinetic energy. From this point here, kinetic energy, Ke, would be equal to, we know that the formula is half times mass times velocity squared. Now we said for this to be escape velocity, that E, or the Ke, should be equal to 0. In this case, the velocity you have here is not just V, but Ve, known as the escape velocity. So we have this case here. If I substitute this value here, you have that Ke, which is simply half mve squared, is equal to the work done. The work done is gmme. That's simply equal to gmme all over r. So we have this case here. All right, so from this question here, our next task here will just simply be to, let's solve this question. Now to solve this question here, let's simplify the left-hand side of the equation. All right, of course, this mve squared would multiply 1, so it becomes 1 times mve squared. That becomes sk velocity squared all over 2. It's equal to g me all over r. So we have this. Now, one of the things to always notice is that if I have the same term, all right, so one thing to always notice is that if I have a particular term on both sides of an equation at the same position, they can always cancel out. So in that case, we are having m at the numerator in the left hand side and also at the numerator in the right hand side of the equation, so they can cancel out. So it means that m will cancel m here, right? Or m cancels m, or m will cancel m. We have that the sk velocity squared all over 2 is equal to g times mass of the Earth all over arrow. So you have arrow there. All right. All right. So if we have this here, what's next? At this point here, let's make arrow E. Let's make VE, that's escape velocity, to be subject of the formula. From here, this cancels this and this cancels this. So I have arrow times VE all squared is equal to 2 times G times mass of the earth. So we have this one here. All right. All right. From here, let's proceed with this. Okay. Our next task here, of course, will be to divide here by arrow. Also divide here by arrow. So divide here by arrow, divide here by arrow. This cancels this. So the escape velocity squared is equal to 2G mass of the earth all over r. So we have this. Okay, the next thing to note is this. If you're considering escape velocity occurs when a body finally leaves the gravitational influence of the earth, which we, in this diagram here, we can simply say from here to this point here, or any of the circumference of the circle. That's from here to here. When a body simply moves from, let's say from the center here, it moves from here till it escapes here up to this point here. In essence, it means that the distance we need is simply r here. That's the radius of the earth. Once a body can surpass the earth's radius, then somehow it can actually escape the earth's gravitational influence. So the distance needed here is actually the radius of the earth. We are saying r is equal to r. So please know why I'm changing this from the normal r to radius of the earth, because once the distance or the minimum distance that the body would cover in trying to escape the earth is just the radius of the earth. But once the body surpasses the radius of the earth, as you can see here at this point here, right, from here to here, see the same thing here. That's the r, radius of the earth. But once it surpasses the circumference and passes the radius of the earth, we can say it has escaped this influence of this earth here. All right, so in that case, r is equal to r. So what do we have from here? From here, we now have that v is squared. All right, so we have that escape velocity all squared is equal to, my formula here is simply 2gme. All right, so 2 times g times mass of the earth all over, without having r here, radius of the earth. All right, so we have this case here. What's the next thing we can get here? Recall from our previous equation, right? Recall from our previous equation that we had that when we try to relate small g with capital G, that was an exclusive video for our channel members. We said small g is equal to g m e all over r squared. So we had this one here as the relationship between small g and capital G. This was done in an exclusive video for our channel members. Okay, it was also derived too. So I'll leave the link to this video in the video description. All right, so you can check out the derivation. Just join the channel membership and check out the derivation. So let's relate this. Why am I bringing this one back here? Because we have to relate this. Let's make ME to be subject to the formula, becomes all over 1. So GME times 1 becomes G mass of the earth is equal to this times r squared. That becomes G times r squared. All right, so we have this case here. Now, if this is true, let's get the value of ME. To get ME, I'll divide here by G. I also divide here by G. This cancels this. So you can see that ME is equal to, look at the value there. So it means that VE squared, escape velocity squared, is equal to 2 times G all over R multiplied by ME. Right? This and the previous one are the same thing. So I'm saying this equation here and this equation are literally the same thing. Okay, let's put in values. This will be equal to 2 times G all over capital R multiplied by, or dot. What's the value of ME, mass of the earth? Mass of the earth is this, right? GR squared. That's G. Now, we'll no longer use the small r. We use what there? The capital R, which is what? Radius of the earth. And I explained why we're using capital R. Okay. Then G all over G. So we have G here. All right, so we have this. Let's solve this question here. From here, we can see that G will cancel G, it's gone. R here 1, cancel R, so we have R here. All right, so it means that VE squared, escape velocity, VE squared is equal to, with this now I'm left with just 2G and R. That becomes 2GR. This gives you 2G and R. Now to get the value of VE, I'll have to take square root. So it means that VE is equal to the square root of 2GR. So what we have here becomes the formula for escape velocity. All right, so this is how we derive the formula for escape velocity. What we said R here is not just any radius, but the radius of the Earth. All right. Now, if this is true, if you have RE as the radius of the Earth and G, small g, is a constant, that means the escape velocity is actually a value. You can get a value for it. Yeah. Now let's get the value of escape velocity. We know that R, radius of the Earth, is simply is a constant, and the value is about 6.4 times 10 to the power 6 meters. And also G is equal to, let's use 9.8 meter per second squared. Let's impute this value into this equation. We'll have that escape velocity VE is equal to the square root of 2 into G, 9.8, into R is 6.4, times 10 to the power 6. Okay, I'll get my calculator. I'll punch this very fast. So we'll have that VE, escape velocity, is equal to, I'll get my calculator, square root of 2 times 9.8 times 6.4 times 10 to the power 6. The value is about 11,200 meters per second. Now, what this simply means, so you have this, what it simply means is that for you to project any body, for that body to escape the Earth's gravitational pull and perhaps launch into space, that body must be projected um, with a velocity of minimum 11,200 meter per second as a minimum. So anybody that is being projected with a velocity above 11,200 meter per second would most likely surpass the Earth's gravitational pull and launch into space. All right, this value is what astronauts use to launch some of the rockets, right, and the space shuttle you see. They are being launched with a velocity that is over this value, that's above this value, so that they can actually go to space. All right, let's give this answer here in index form. From here, we're having 1, 2, 3. That becomes 11.2 times 10 to the power what there? 3 in meter per second. But we already know that 11.2 times 10 to the power 3 is, or 10 to the power 3 is called a kilometer. 10 to the power 3 is equal to a kilometer, which is K. So this is equal to 11.2 times 10 to the power 3 becomes kilometer per second. All right. So for a body to escape the Earth's gravitational pull, it must be launched with a velocity of 11.2 kilometer per second or something above this. All right. So this is how we work on escape velocity. All right. So this is how this works. All right. All right. Don't forget, you can always get more videos like this on my website. Visit www.jonahemmanuel.com/courses, or you can subscribe to my exclusive videos, all right, by joining my channel membership. All right, I'll leave a link to join my channel membership. So click on the link, look at the different channel membership packages. You can choose any one and then learn from it. All right, or of course, visit my website, www.jonahemmanuel.com/courses, to check out the available courses, or /books to check out the available books. All right. If you enjoyed this video, as usual, please hit the like button. All right, like this video, leave a comment. If you have any questions, leave them in the comment section. If you enjoyed this video, tell us in the comment section. If you're yet to subscribe, or if it's your first time, please do want to subscribe to this channel and hit the bell icon so that you get notified whenever we upload new content. And finally, always share this video to your friends so that they can also learn. Thank you, and see you in our next class.